This video is all about the Doppler effect, a very important effect that can occur with sound or with light. Of course, we'll be looking at its effect with sound in this video. The Doppler effect is a phenomenon where even though the frequency and pitch of a source remain constant, so like a bell or a siren may be emitting the same frequency the entire time, someone will observe that this pitch and therefore frequency seems to be different. It occurs when either the source or the observer, or sometimes both, are moving. One is moving relative to the other, or both are moving. Depending on how they're moving, you may measure the frequency to be less than is being emitted or greater than is being emitted. So why is this so? Let's take a look at this diagram, which will help us understand it a little bit better. Here we have a stationary source and a moving observer. You'll see that the wavelength of that source is constant, and therefore what is being emitted is constant. But the biker in the picture on the left will experience those wave fronts more frequently than if he were standing still. Because he experiences those wave fronts more frequently, the frequency of the wave that he hears will be higher. Let's take a look at the picture on the right now. The observer is moving away from the sound source. Because he's moving away, he's going to experience those wave fronts less frequently, because they're going to have to catch up with him. And so the frequency of the sound he hears is lower. This can be described with the following equation. F sub O, the frequency heard by the observer, is equal to F sub S, the frequency of the source, times the quantity V, or the speed of sound, plus the speed of the observer, divided by the speed of sound minus the speed of the source. Now, there are some rules for plugging numbers into this equation that are very important. If the observer is moving toward the source, the speed is positive. If the observer is moving away from the source, the speed is negative. In other words, we'd plug in a negative number for that speed. We wouldn't change the equation at all. The same thing goes with the source. If the source is moving toward the observer, then the source is positive. If the source is moving away from the observer, then the source speed is negative. If they're both moving toward each other, then both of their speeds are positive. If they're both moving away from each other, then both of their speeds are negative. It is also possible for one to be moving toward one, and the other one is moving away from the other. An example of that might be if one kid is shouting at another. Let's say the kid in the back is doing the shouting, and the kid in the front is running away from the kid who's doing the shouting, but the kid who's shouting is running toward and trying to catch up with the one who's running away. You'll see one is running away while another is running toward. That's probably the hardest thing about these problems, is deciding what the sign should be of the speed. So let's take a look at a few of these problems. Starting with example number 3. An airplane traveling at half the speed of sound emits a sound with a frequency of 5 kilohertz. At what frequency does a stationary listener hear the sound as the plane approaches and after it passes? By the way, this phenomenon, the Doppler effect, is often observed when you hear an ambulance coming toward you or going away from you. If you are stationary and the ambulance is moving, while that ambulance is coming toward you, the frequency sounds higher. But as soon as it passes you and is then moving away from you, it sounds like the siren has changed. Really, it's just the observed frequency that has changed. Okay, so we're going to start this problem by writing out what we know. Just because with so many different speeds in this equation, I think sometimes it can get a little bit fuzzy as to what we know. So we know the airplane is the thing emitting a sound, and it's traveling at a speed of 172 meters per second. So that's the speed of the source, 172 meters per second. We know that an observer is stationary. It says a stationary listener. So the speed of the observer is 0. We know that the frequency of the emitted sound, that's going to be the frequency of the source, is 5 kilohertz, or 5,000 hertz. We also know that when we're not given anything about the temperature of the air, we assume the speed of sound to be 343 meters per second. We're trying to find the observed frequency. The first one is as the plane approaches. So in part A, the speed of the source is going to be positive, just as I have written here. Our equation is that the observed frequency is the source frequency times V plus VO divided by V minus VS. I can just plug some numbers in. 5,000 hertz times the quantity 343 meters per second plus 0, because my observer is not going anywhere, divided by the quantity 343 meters per second minus 172 meters per second. This gives me a frequency of 10,030 hertz, or I could leave that in kilohertz like the original answer was. So the observed frequency is 10.03 kilohertz. That's when the plane is approaching the observer. Well, what changes if the plane is moving away from the observer? If the plane's moving away, we're going to do that in black here. Then this source is moving away, so it would be negative 172 meters per second. So I'd plug in negative 172 here, so 343 plus 172, since the negatives cancel each other out in a way. In that case, the frequency becomes 3,330 hertz, or 3.33 kilohertz. The really nice thing is that you can check your answer with the Doppler effect. If the two objects are getting closer together, the observed frequency should be higher than the source frequency. If the two objects are getting further apart, then the observed frequency would be lower. Let's try another one. In this one, two trains are moving toward each other. Train 1 has a speed of 130 kilometers per hour, and train 2 has a speed of 90 kilometers per hour. Train 2 is the source. It emits a sound of 500 hertz. We want to know what is the frequency that's heard by the engineer on train 1. Okay, so again, I'm going to write out what I know already. I know train 1 is the observer. So the speed of the observer is 130 kilometers per hour. And the speed of the source, train 2, is 90 kilometers per hour. I know that the source frequency is 500 hertz. And lastly, I know that the speed of sound is 343 meters per second. Now here's the thing, all my units don't match. Hertz, I know, is 1 over seconds, and the speed of sound is meters per second. But my other two things are in kilometers per hour, so I need to convert those. 130 kilometers per hour is the same thing as 36.11 meters per second. And 90 kilometers per hour is the same thing as 25 meters per second. Now that all my units match, I can plug into my equation. Before I plug anything into an equation, though, I'm always going to stop and make sure that I have the sign of my speeds correct. It says that these two trains move toward each other. Therefore, both speeds should be positive, just as I have written here. Now that I've checked that, I can move on. The observed frequency is the source frequency times the speed of sound plus the speed of the observer divided by the speed of sound minus the speed of the source. All I have to do is plug numbers in again. So the observed frequency is 500 hertz times the quantity 343 meters per second plus 36.11 meters per second divided by 343 meters per second minus 25 meters per second. Once I plug all of that into my calculator, I get a frequency of 596.06 hertz. I'm going to stop and ask myself, does that make sense? Should my observed frequency be higher than my source frequency? As a matter of fact, it should, because these two objects are getting closer together. So the observed frequency will always be higher if they're getting closer together. That's the end of the video on Doppler effect. Hopefully, you were able to understand it. If you have any questions, bring them to class.